All right, so welcome to 4.8. We're going to be analyzing lines of best fit here. We created these lines in scatter plots in an earlier lesson. So we're going to write a linear function here. We have height, and I unfortunately use h of h, which is not my favorite, but we're height as a function of ours for this plant. So we need two things, right? We need our y-intercept, which would be right there. And it seems like the boxes are going up by 2, 2, 4, 6, 8, 10, so on. So then we have a plus 4, and it says it's inches, so it's 4 inches. Now we have to figure out a slope. Okay, so let's look for some good intersections. Yeah, I'd say here looks good, and here looks good. Yeah, so I'm going to say, right, I like to make a pattern to make sure I have a good idea of what the slope is. So the rise here is, oh, no, I almost said 3, but each box is worth 2, so the rise is 6. Along here, each box is worth 1, it's 2, so it's 6 over 2, the slope is 6 over 2, which is 3. And so h of h equals 3h plus 4. Please, Mr. Ben almost made the single most common mistake with this, right? You can't just count boxes when it's a real world graph. All right, the line of best fit we drew in an earlier lesson to be following the pattern of the points, trying to have about half of them above and half of them below. The distance between the point and the line is called the residual, all right? And when we pick our line, we're trying to pick a line that makes those residuals as small as possible, okay? So we're going to add up the residuals in this one. So we have 0 plus negative, I'm adding up this column right here, the residuals. And that's these distances. Some of them are positive when the line is below the dot, and some of them are negative when the line is above the dot. So let's just show you this. So this first one is 0, 20, it's this one, right? And it's right on the line, so it has 0 residual. Then we have this one at 20, 20, that's the second one, and it's 7 below the line. And so it has a negative residual. Then the next one here is right there. That's 35 and 50. And that has a positive residual of 18. All right. And so what I did was I took all the residuals for all the different dots, and then we're going to add them all up. Let's see. So negative 17 plus 18 is 11, plus 5 is 16. Oh, they add up to 0. And it turns out, so that is the line of best fit, right? All the residuals added up to 0. If I made a line a little higher, the residuals would not add up to 0. There would actually be a negative residual number down here. And if I had made it too low, there would be a positive residual sum there. What we want is this line to all the residuals to add up to 0. Okay. All right, so when we calculate the exact line of best fit through a mathematical process, it's called linear regression. We're making a line by doing a series of calculations that calculate that line of best fit. We estimated it in class, but there's actually programs and formulas to do that. And you'll go through those processes in high school. In Algebra 1, we just want you to be able to look at a calculator and have the calculator do the linear regression for you. I'm sure you're glad about that. But you have to be able to read the output from your scientific calculator. Now, one of the things is, right, we've been using y equals mx plus b. All right, but calculators use a more general form, which you will see in high school, and they use y equals ax plus b. A is the same as m. It is the slope, right? So it says find the slope and y-intercept. So the slope here is 4.1, right? And the y-intercept B is not the y-intercept. The y-intercept is 0, 18.2. All right, and so then to write a linear function for this, it'd be y equals 4.1x plus 18.2. All right, that's how you read that. And we're going to be doing that with the calculator. All right, find this one. Now, same thing. Now, one of the things we're going to realize is that in the real world, you get wacky numbers. So I'm going to ask you to round to the nearest tenth. That's just Mr. Ben deciding to do it that way. All right, but we don't want to write a linear function with negative 0.8. That's, by the way, negative 0.8 with 3 repeating there. We don't want that to be our slope. All right, so we're going to look at the hundredths place, realize it's a 3, and we're going to go negative 0.8, right? If it was 0.5 repeating, we'd go up to 0.9, or we go to negative 0.9. So negative 0.8x plus, and again, we're going to round to the nearest tenth. So we look at the hundredths place. It's a 2, so we're going to stay there, plus 9.4. And I probably should use an approximate symbol here since I'm writing an approximate line there. But if we graph that, that will be the line that best fits the data. Okay, that is the formula for this line of best fit through linear regression. And so when you see this on the calculator, LinReg stands for linear regression. So we want to know how well the data correlates, right? No matter what data you put into the calculator, it will give you a line of best fit. But as we learned earlier, that line of best fit may make sense or it may not make sense. And so if it makes sense, we say the data is strongly correlated. If it doesn't make sense, we're going to say it's weakly correlated. All right, so is this data here strongly correlated? So when we say correlated, it means the data and the line we drew are close to each other. Is that true here? Right, we studied minutes, how many minutes you studied for a test versus the score on the test, and we would say this is strongly correlated. All right, these data points, most scientists would be ecstatic to have data points that close to their line. All right, then we did a data graph of hours of sleep versus pool usage. And remember we said that sleep had nothing to do with whether you went to the pool the next day. And so what we get is a bunch of stray dots. Now, if you put those stray dots points into the calculator, you will get a line that will be in the middle of them. But it's not going to tell you anything because this is weakly correlated. Okay. So you have to be careful. Is your line really valuable or not? Luckily, the calculator will also tell you whether it is valid correlation or not. All right, so we're going to do that with something called the correlation coefficient. So let's look at our data here. So we have y equals ax plus b. It says examine the calculator output. Write a linear function for the data and determine its strength. So let's start with the part we already know how to do. We're going to round this, right? We're going to look at the 6. So 6 means make 3.9 go up, right? So we're going to go y equals 4, right? Because 6 is 5 or bigger, you go up. So y equals 4x, and we're going to look at that. And it's negative, so it's minus 7 there. Okay. Now, the correlation coefficient is r. We're going to that gives you something called r squared, which is called the variance, which you'll use in high school. For today, we're just going to use r. So just every time you get the output, you cross out r squared and look at r. Now look at r. It says 0.94298338666. And that actually may be much longer. The calculator just ran out of room. Now, what is the code here? So I want you to write this down. So if it's positive 1, it is strongly correlated. If it is negative 1, it is strongly correlated. All right. If it is near 0, it's weak. Okay. Because remember, we can have slopes that are both positive and negative. So when the slope, if it's positive, you had a positive slope. Now we had a positive slope here. So the correlation coefficient is going to be between 0 and 1. So tell me, 0.94, is that closer to 0 or closer to 1? Hopefully we're saying closer to 1. And since it's closer to 1, we're going to say it's strongly correlated. So what this calculator is telling you in this data is that we calculated a line of best fit. This is its equation, and it's a good equation because this is extremely high. Scientists wish they got correlation coefficients of 0.9. That means it's almost right on the line the whole time, right? Because 1 would be perfectly on the line. Let's look at the next one. So write your equation, rounding to the nearest tenth. So we're going to write y. So we're going to look at the hundredths place. It's a 9. So once again, we're going up. So y equals 1.4x, right? And we got a minus there again. And then we're looking at a 9. So we're going up to 3.9 minus 3.9. All right, so now we cross out r squared. Now let's look at r. R is 0.29. Right, which rounds to about 0.3. So is that closer to 1 or closer to 0? And it is closer to 0. So we would say this is weakly correlated. So that means that this data, although we got an equation, these dots are not all that close to the line. Okay? And so you should be, is this line going to be good at predicting the future? Probably not. This line over here that's strongly correlated, is that going to predict future behavior? Probably very well, since so far the data we have is right near the line. Okay, all right, so let's look at this. The data has a negative slope, it has a negative correlation. Perfectly correlated data has a correlation coefficient of -1, and values near 0 still indicate a weak correlation. All right, so looking at that, is that strongly or weakly correlated? It is strongly, okay? Right, because those dots are very close to the line. All right, watching TV apparently has a, right, the more you, this is a negative slope because the more you watch TV, the less well you do on a test the next day, okay? That's what that's showing. All right, so here's the output for this data. So we get y equals, right, well, I didn't ask you to do this part, but so we look at 3, you got -17.5 plus 96. Notice it's a negative slope, right? Right there. A is negative, okay? And that means it has a negative slope. And look what happened to the correlation. The correlation is negative. Negative is not bad. It just, anytime you have a negative slope, you're going to have a negative correlation. But is that close to -1? Sure is. All right? And so this is what strongly correlated data looks like coming out of a calculator. All right, so you're going to sketch these and then you're going to tell me positive correlation, negative correlation, or weak correlation. We'll see that. All right, so hopefully the easy one is the one in the middle, right? That's a scatter of dots. That's weak correlation or weakly correlated. I can say it that way, weakly correlated, right? Look at this. This is going down. So this is a strong negative correlation. The dots are near the line, right? But it's going down. Why is that? Because the more you exercise, the lower your body fat usually, all right? All right. And so more of the exercise makes less of the body fat or vice versa. And then this one, although you might say that it looks curved, but let's assume that it isn't. You could follow a straight line here, although you might want to go curved. I'm going to say it's a straight line. More of the temperature creates more of the pool usage, and so we're going to say this is a strong positive correlation. More temperature makes more people go to the pool. All right, and so those are the 3 possibilities. So from this data, we have to write a line of best fit. So remember, Mr. Ben wants us to round to the nearest tenth. So we have y equals, And this is a 5. So we're going to go up and round that 7 up to 8. So y equals 7.8 x. There's another 5. So we're going to round that 7 to another 8 plus 15.8. It's our line of best fit. We're going to ignore the variance, r squared, and we're going to look at r. Now, this, would never put this on the test, but what did we made the rule that if it was closer to 1, we were going to say strong, right? And it was closer to 0, all right, you were going to say weak. Now, 5.1 is almost in the middle, but it is slightly closer to 1, so we're going to write strong here, although it's not that strong. Right, this is a strong correlation just because it's closer to 1 than it is to 0, because 0.51. Remember, if it's strong, closer to 1 or -1, it is strong. All right, so the same thing here. This time we have a 7 here, so we're going to go up to, now this is a negative slope, and that means we're going to have a negative correlation as well. So negative 8.1, because the 7 makes the 0, 1, x plus, we have a 5 there. Again, we're going to go up to 48.4. All right, we're rounding to the nearest tenths I want. Correlation, so negative 3.6. All right, so that is there, right? It's closer to 0, all right? It's not weak because it's negative. It's weak because it's closer to 0, right? Right. Negative 0.5, we had a negative 0.51, we would be strong. This is a weak correlation. All right, so if you have a TI-84 calculator, this is how to do a line of best fit. So if you have one, you can get it out. You press the stack key, then press enter after you press the stack key and go to number 1, edit. Okay, you enter your x values. All right, it goes down. You do all your x values first. All right, and you press enter each time, it will go down automatically. Then there's a right arrow key over on the upper right part of your keyboard there on the calculator, and that will bring you over to the y's. They call this L1 and L2. You'll enter your data. It will move down the list as you go. When you're done with all that, you press that same stack key again, and then you press this right arrow key that you used before, and so you'll move over to calc, as in calculate. And you press the down arrow 3 times, and you will all of a sudden see this, LinReg, linear regression, AX plus B. You press enter twice, and data should appear. Okay, and you'll enter it right there. Good luck.